Okay, guys, so I'm recording now. Welcome back. We just started thermochemistry this week, so some of you have already had your lab on thermochemistry. It's just kind of the way the course works that it's not necessarily caught up with the labs, but I think by the time we get to reaction rates, which is your lab after sports day, so like middle of February, you'll notice that it kind of makes sense. It's caught up. So last day we were talking about thermochemical reactions and what that means and what heat is. And I very quickly kind of went over this topic. This is a topic from Chemistry 1120 in Unit 5, where we talk about how do you know if a chemical reaction happens? There's many things that explain if a chemical reaction happens. Is there a color change? Is there a gas formed? Is there a precipitate, a solid formed? And another one is there a temperature change? And like for me personally, when I think of chemical reactions, sometimes I think of them like, oh, well, they get hot, they get warm. Well, they can also actually get cold as well, and it's a little more rare. Like you don't see this, or I personally haven't seen this as much in the past as chemicals getting cold, but it does happen. So there's two ways to classify a thermochemical reaction. It can feel cold in your hand, or it can feel hot in your hand. Or I guess maybe we shouldn't be talking about your hand, but like if you put a thermometer in that reaction, it would either get hotter or it would either get colder. And again, typically you tend to see them get hotter. So endothermic is a term that refers to chemical reactions that feel cold. The heat of this, now this is a really, and I didn't really get into this yesterday because we were running out of time, but it's a really interesting thing to think about. Endothermic feels cold, which means the heat of the system increases. Now remember, when you're looking at a chemical reaction, you are the surroundings. Okay, so when you're in the lab, when you're working, in the field, again, I don't know what program you're in medical science or engineering, but when you are working in the field, you are the surroundings. The system is typically the chemical reaction that you're observing. So when I say that endothermic feels cold because the heat of the system increases, that's because the system is absorbing energy or heat from your hand. So it's kind of like when you pick up an ice cube, right? If you held an ice cube in your hand, it would feel very cold. Why does it feel cold? Well, it's because you are a warm body, you're a warm person, 36 or whatever degrees Celsius. The heat from your body is leaving you and transferring into that ice cube. So the ice cube feels cold because the ice cube is absorbing energy from your body. Exothermic is the opposite. This is when you pick up something that is warmer than your body. So you pick up a hot coffee mug, or you put your hand over a candle that's burning. That feels hot. The system is losing heat to warm you up. It's a little kind of weird to wrap your head around, but I have an example here. And I'll make this full screen on the next section. I have the next section opened up in PowerPoint, but there's I want to say three reactions or three examples here. If you guys could, in the chat, let me know what you think. A, B, and C. If you put your hand around an object. Now, C is going to be a little bit of a thinking question. So if you don't know C, don't worry about it. But I'm going to give you a minute in the chat to tell me if A and B, especially A and B, are endothermic or exothermic. So you can answer that in the chat, and I'll be right back to see your answers. Okay. Yeah, okay. Oh, Aisha, I think I'm saying your name right, Aisha Norin. You got C correct. Okay, so let's look at all this. Um, Fire, obviously exothermic. You know, think about it. If you put your hand over the fire, it feels warm. That chemical reaction is releasing heat, giving up heat, which means it's exothermic. The heat is exiting. Cold packs are endothermic. If you hold onto a cold pack, your hand gets very cold. That's because your hand is giving energy to the system. Temperature is going down. It's absorbing energy from you. So endothermic. Again, think of those words. Exothermic, heat released. Endothermic, heat absorbed. And that's kind of what brings me to C, is this concept of in photosynthesis, think about sunlight as energy. Well, I mean, I shouldn't say think about sunlight as energy. Sunlight is energy. So are plants releasing the energy, or are they absorbing energy from the sun? And the answer, and I think a few people got this right. I know I looked at the chat and Aisha got this right. Let me just check the chat again. And Harold and Yasmin got it right as well. I'm sure there's more people. I don't mean to exclude. Iman got this right in the chat. The plants are absorbing sunlight, right? So photosynthesis, it takes water and oxygen and sunlight. I guess in biology, it's just sunlight and oxygen. It absorbs those things, so it's endothermic. That's good. So for those who have no idea, I'll just write the answers here. So fire is exo, cold packs are endo, photosynthesis is endo, because they absorb energy, and the fire, of course, releases it. Cool. I'd say most of you have done your labs so far. Your labs, I think, I haven't taught chemistry 1120 labs in a couple semesters, but I'm pretty sure in your labs you guys do an endo and exothermic reaction, so you would see both. So I'm going to move into part 2 of Unit 2. The way Unit 2 is formed is, or outlined in the notes, is I kind of skip around a little bit. We're going to do all of Unit 2, but I'm going to kind of skip through some objectives so that it kind of matches a little bit better with your labs. So today, depending on the time, it's 11:48. I'm going to hopefully get through most of this concept of calorimetry, which is what your lab this week was on. So your student, or any students who've done the lab, you've seen this calorimetry concept. I'm just going to pause here. I just got to run to the door. I have a water delivery man here. I'll be back in 1 second. Okay, sorry about that. So thermochemistry, again, I told you guys the other day, this is definitely one of my favorite topics in all of chemistry. Because it's basically cooking. And, I made the joke that cooking is probably like one of my favorite things in life, even though I don't do it a whole lot, with Talabat and Carriage and all those apps. But I mean, all I do is watch videos, or I love the whole concept of cooking. And it's all related to physics and chemistry. The idea of heat transfer and how it changes food is really amazing. So One thing about that that we need to consider is, how do we measure the heat in a chemical? So the heat of a chemical reaction, how can we measure that? Well, we can use calorimetry, and think of the term calorimetry and think of a word in your day-to-day life, or a word that you've heard before that is similar to calorimetry. You should be thinking of, if you've heard the word, I'm going to check the chat before I say the answer. Yeah. Excuse me. Calories. Oh, and Abdul Rahman has a good answer in there as well about how do we measure heat changes, because he's talking about the mass of the system or the mass of the water. We'll get into that. But Aisha and Iman, yeah, calories. Calories are the measure of the energy in your food. And like I'm not a nutritionist, I'm not a biologist, but the whole idea of gaining or losing weight in your body is making sure that you burn more calories than you are eating. So this is the law. This is one of the first laws of thermodynamics. So when you're thinking, if any of you guys want to lose weight, or maybe you want to gain weight, you want to bulk up, it's chemistry, it's science, it's the first law of thermodynamics. If you want to lose weight, you eat less energy than you use. Okay, and by burning, they say burning calories, by using up these calories, you create like a deficit. It's an imbalance, and you should, in theory, lose weight. So calories are related to energy, and calorimetry, metry meaning measure, is the science of measuring energy changes. Now, there's no magical device in chemistry that will measure an energy change. In terms of like heat, we have a device that measures temperature, and that's where calorimetry comes from. And so Naraz in the chat mentions gaining muscle, not fat. Yeah, I won't get into that because that's a whole other biochemical thing. To gain muscle, you have to intake a lot of calories, but then you have to convert those calories into muscle by actually doing something. But again, that's biology, but so I won't get into that. Because honestly, I don't know much about it. So calorimetry is the science of measuring energy changes, and the only way, the simplest way we can measure an energy change in the lab is with a device that's hundreds of years old. It's a thermometer. Easiest device ever. It measures changes in temperature. So if I want to measure energy change or heat change, I can study temperature. One important thing, and guys, I'm going to wink, wink, wink here, is that, hold on, let me get my pen here. Is it not going to let me write? Oh my gosh. Hold on. My pen's not working. This is my nightmare. Okay, hold up. I'll get this going. There is an outcome in this course that asks you to know the difference between a simple calorimeter, what we would call a coffee cup calorimeter, which this is what you do in lab 1, and a bomb calorimeter, which is kind of exactly what it sounds like. You kind of like make an explosion in a device. And you really, like, wink, 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 you need to know the difference between the two. And I can definitely explain this. All right, well, I hope I can explain this. A coffee cup calorimeter is at constant pressure. What that means is the coffee cup calorimeter is not a very good closed system. You're opening the coffee cup, there's a lid, you're changing the volume, you're pouring liquids in, you're stirring it, there's air getting in, and it's not a perfect system. But what that means is a coffee cup calorimeter is at atmospheric pressure. It's at constant pressure. A bomb calorimeter, however, is a closed or isolated system. Like it's extremely isolated, like you would think of like a thermos or something, or even like a vacuum sealed bag you would get food in. A bomb calorimeter, and I'm going to show you a picture in a minute, is at constant volume. So it's like, I know you guys are going to get confused about this, or I think you might. But the coffee cup is technically open. Now, I know you put a lid on it, yes. But with the coffee cup calorimeter, and you'll see this in the lab this week, I know some of you have already done the lab, you're adding material to it. You're pouring in liquids, you're stirring it, there's air getting in and air getting out. I mean, it's a coffee cup. You can drink out of it. So the coffee cup is open, which means it's at constant atmospheric pressure. So whatever the pressure is in Doha at that time, that's the pressure of your calorimeter. A bomb calorimeter is a crazy device. It is like isolated, inches of steel. It's sealed, screwed together tightly. The pressure inside can change, but the volume itself stays constant. Once you set up the bomb calorimeter, you cannot change the volume. It is a closed system. And I have a picture of that right here. So like, look at how intense this is. Now, guys, you do not need to know how to label this. You don't worry about this slide. All you need to know is that a coffee cup is constant pressure. A bomb calorimeter is constant volume. This system is completely closed. Unlike a coffee cup, we can't take the lid off. We can't add volume. It's completely closed. And why do we call it a bomb calorimeter? We literally ignite or explode. Like you blow up a sample inside the calorimeter, but it's like inches of steel thick, and it measures the temperature change of and actually, this is a good little learning point here. This is my system. This is my surroundings. So the thermometer is in the surroundings. We measure the temperature change there, and we can figure out heat. And by figuring out heat, we can also figure out calories. So sorry, let me get my pen here. I got some messages in the chat. Yeah, so for Amman, the what you did in the lab where you added like the solid and HCl, that's coffee cup, that would be constant pressure. But because you're adding chemicals, it is not constant volume. So what you did in the lab, or for some of you who have a lab after this, what you're going to do in the lab is constant pressure. Constant volume, meaning we can't change anything, is the bomb. And Aisha mentions in the chat, do we need to study this diagram? No, do not study this diagram. I will not ask you about this diagram. And Abdullah in the chat asked, so the bomb is better to measure? Yes. The bomb calorimeter, it's not easy. You need special equipment, but the bomb is definitely much better. There's less error because you're not losing volume. It's a closed system. The bomb is definitely more precise and more accurate. So typically, when you guys eat potato chips, if you're anything like me and you like potato chips or nachos or, Skittles or, and candy, how do they find the calories of a piece of candy? How do you know the calories of, say, like a date or an apple or a potato chip? They literally blow it up in a bomb calorimeter. They burn the chemical, they burn the food and measure the energy that's released. It's really cool. I think it's cool anyways. Okay, so just give me 10 more minutes here and we'll finish. I kind of want to get into the calculations. We might not get to do the calculations today, but we'll get close. The interesting thing about calorimetry is every substance has its own heat capacity. Now, what is heat capacity? This is a really interesting concept. Heat capacity is how many joules of energy it needs to raise the object 1 degree Celsius, or more specifically, wink, 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 wink. What you really need to know in this course is this term called specific heat capacity. This is how many joules of energy it needs to make 1 gram of that chemical raise 1 degree Celsius. So notice the difference between these definitions. Heat capacity doesn't have grams. Specific, and again, think about what that word means in English. Specific means, like a clear definition. Specific means we're going to consider the mass. So wink, wink, wink. Definitely know this. Specific heat capacity is how many joules of energy it needs to make 1 gram of chemical raised 1 degrees Celsius. Specific heat capacity, the symbol for that is C, which kind of makes sense because it's, capacity. And the units are joules per grams degrees Celsius. Now, hold on, give me 1 second here. I want to see what's on the next slide before I explain this. Okay, I'm going to have to explain it. Or, well, I want to explain it. I shouldn't say I have to, but I want to. In the blue here, let me clear my writing. Oops. I don't know why it's not letting me draw on my PowerPoint today, but anyways, in the blue here, this is the specific heat capacity of water. Water has a heat capacity or specific heat capacity of 4.184. What this means is it takes 4.184 joules to heat 1 gram of water 1 degree Celsius. Now, what does this even mean? What does heat capacity mean? I'm glad, Iman, I'm glad something is making a bit of sense in chemistry, finally. Chemistry is such a weird science. I told my class last year, and I tell most of my classes, if physics didn't have so much math, I'd probably be a physicist. Like I'd study physics, because physics to me makes the most sense. It's just the math is crazy. At least chemistry isn't all math. Anyways, heat capacity. I want you to think about, how am I going to work? Well, okay, think about 2 situations. This will be a little bit morbid or a little bit dark, but imagine on your stove, you have boiling water at 100 degrees Celsius. Okay, so boiling water on your stovetop, 100 degrees Celsius. Now, think about your oven. Imagine you're baking a cake, or you're baking nuggets, or heating up French fries or whatever. And you set your oven to 200 degrees Celsius. Okay, think about those 2 situations. So there's a pot of boiling water on your stove at 100 degrees. Your oven is set to 200 degrees. Now imagine putting your hand in both. Put your hand in the boiling water, put your hand inside the oven. Don't touch the metal, that's different, but put your hand in the oven. Why is it that in the boiling water, you would probably have to go to Hamad or Al Ali or wherever hospital because you burned your hand? But how come you can put your hand in a oven that's twice as hot, 200 degrees Celsius, and you can put your hand in that oven, and you could put it in there for well, maybe not 5 minutes, but 10, 15, 20 seconds, and it wouldn't bother you. What's going on? 100 degrees, 200 degrees, it doesn't make sense. And the reason you can stick your hand in the oven is because of heat capacity. Water has a very high heat capacity, which means water absorbs, I'm going to get back to the comment in the chat in a second. Water absorbs a lot of energy. Air does not absorb a lot of energy. So the heat capacity of water is 4. The heat capacity of air is 1. So you can put your hand in a 200-degree oven because the air does not absorb as much energy as the water when you heat it. Again, it's all about energy, right? So even though the temperature is 200, the energy is not as high. I don't know if that makes sense, but I always found it kind of interesting or kind of amazing that you could put your hand into a 200-degree oven and it's not like putting your hand in boiling water. And it's all about the energy that they absorb. Aman mentions in the chat, I am a math teacher and I do like math, but the math that I like is different than physics math. Like physics math got into calculus and integrals and differential equations, and the math in physics is not the math that I like. I kind of tend to like algebra, geometry. Yeah, physics math is a demon, as Yasmin says. It's a lot different than algebra or something like that. Once you get to higher levels, physics math gets crazy. And any of you guys going on to university or moving into other programs, you'll see it. It's calculus, integrals, differential equations. It's crazy. Anyways, okay. So guys, I'm going to finish on this slide today. And any of you guys who did your lab this week, you've pretty much seen this. I do apologize that the labs are going a little faster than the course, but we should be caught up very soon. But I want to look at this example. And then that's it. Halas, we're done. Calorimetry uses a very special equation, probably one of my favorite equations in all of chemistry. Q, which is heat, equals mc delta T. Q equals M. I used to say this when I was a chemistry student. Q equals MCAT, because the C delta T looks like the word cat. So Q equals MCAT. But by the way, all of these formulas are in your data booklet, so you don't need to memorize these formulas for your tests or final exam. They're all in your data booklet. So let's look at this formula. Heat is Q. Q is heat. M is the mass of your system. Let me write that down. That's really important. C is your specific heat capacity. It's usually the same as water. And excuse me, and delta T is your change in temperature, T2 minus T1. This formula is how we can measure the heat in a system. We take the mass of the system, we multiply it by the specific heat capacity. Typically, it's the same as water. I should have said here, typically. Okay, it's not always the same as water, but wink, wink, wink. For chemistry 1121, it's basically the same as water. And delta T is the change in your temperature. So there's an example here on the bottom. 50.4 grams of water decreases from 20 degrees Celsius to 17.2 degrees Celsius. How much heat is released? So Q equals mc delta T. So the mass is 50.4 grams. C is 4.184 4 joules per gram degree Celsius. Now, some of you guys might be thinking, whoa, 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 where did that number come from? That is a constant like gravity or pi. 4.184 is in your data booklet, and it's the heat capacity or specific heat capacity of water. And then I multiply that by my change in temperature. It's always the final, always the final minus the initial. Excuse me, sorry. That's really the most important part here. It's final minus initial. That is so important because that will tell you if Q is positive or negative. Excuse me, sorry. So the final is 17.2, and I'm going to subtract from that 20. I cannot stress this enough, guys. Final minus initial temperature always. The sorry, like I'm stuttering because it's so important. The temperature change tells you if the Q is positive or negative, and that tells you if it's endo or exothermic. So this is like so important. So let me just do this on my calculator here. And by calculator, I mean phone. So my delta T, my change in temperature is negative. The temperature went down. So that means my Q is negative, which means it's going to be exothermic. We'll talk about that more next week. But I'm going to multiply all this together, and I get my answer. Q is negative. You like, this is so important. You need to include the negative. 590.45. This is not the correct significant figures, but I'll fix that in a second. Joules. So in terms of significant figures, it's negative 590. Oh, that's it. We can only have, actually, hold on. Don't worry about significant figures, guys, in this course. That was from Chemistry 1120. We can actually only have 2 significant figures. So this is negative 590 joules. 2 significant figures. Again, don't worry about sig figs in this course. It's not a big deal. Your labs, I would be careful with sig figs, but in the tests and final, I don't care. So there you go. Just don't write like 1,000 numbers, please. Aman said, is EXO? Yes, this is EXO. Hadil asked a question that I knew I was going to get. How did we get the value for C? C is a constant, and it's the heat capacity of water. It's in your data book. Oh man, I'm getting some really good questions here. Abdul Halim asks, is this Q reaction or Q system? Awesome question. This is Q system. Okay, in this example, this is Q system. Okay, so let me kind of address the questions again. As Aman asked, yes, this is exothermic. Heat is being released. What was the other question? Oh, where did C come from? C, heat capacity, is a constant for, and we will wink, wink, wink in this course. You always use water. So 4.184, like you can think of C as like gravity or pi. It's a constant. And Abdul Halim, this is Q system. Q reaction is, and Harold, another good question. Q reaction is directly related to Q system. You just switch the sign. So Q surroundings here, or sorry, Q reaction, Q systems are the same. Q surroundings here would be something else. We'll talk more about that next week. I do apologize that your lab is a little bit ahead of class, but Miss Michelle said she'd help you out. Yeah, so Aman, another good question. In the lab, you guys didn't have water, you had HCl and solid. So why are we using, and this, Abdul-Rahman, this might answer your question as well. This is, before you guys go, this is a really good question because you'll see this on your test, wink, wink, wink. So as Aman and Abdul-Rahim are asking, we're talking about C, heat capacity. And in the lab, you had water and solid. That's, or sorry, hydrochloric acid and solid. That's obviously not water. But in the lab, you used what we call an aqueous solution. So that hydrochloric acid, aqueous, AQ, if you remember that from 1120, is mostly water, like 99% water. So, you know, in physics, when your instructor asks you to calculate the velocity of a football or a bullet, you always ignore things like the resistance of air. You ignore wind, you ignore, you know, so much. You ignore all these factors. Well, in chemistry, we ignore factors such as things that are not water. What I mean is, if the hydrochloric acid is mostly water, which it is because it's aqueous, we make a scientific assumption. And our assumption is that the specific heat capacity is the same as water. Now, that's not true. It's not perfect, but it's close. And science is all about assumptions, you know, especially first and second year chemistry. We're not going to worry about the friction of air. I'm not going to worry about the heat capacity of a few moles of hydrochloric acid. We make an assumption to help us. And that assumption is that the heat capacity of an aqueous solution is the same as water. I promise you guys, I'll explain this better, and I'll talk more about this on whenever we have class next, Sunday or Monday, I can't remember. But next class, I'll talk more about this. Okay, guys, so I'm going to finish here today. If there's any questions, you guys let me know. Other than that, have a fantastic weekend.